All right, friends, the next shape we're going to explore a little deeper is the limaçons, oui, oui. I don't know. Okay. So the limaçons can be tricky because there's different types of limaçons. I think it's important you know the cardioid, which I'll get to in just a moment. But for just your general understanding, the limaçon is when you have like a number plus another number times the cosine, or a number minus another number times the cosine or sine. So if you could, in your GeoGebra grapher, or grapher, whatever you're into, if you could please type in the equation 2 plus 3 sine t. Obviously pause the video at this time because if it takes you a while to do it, just get it graphed and just make sure that green circle is at the y-axis. So after you graph this one, you're going to see that the graph actually starts when theta is equal to 0 at 2. But that's not the maximum of this. Note that the maximum R value is going to be when we hit this value of 5. Now, why 5? Because think about what is happening with that midline at 2 and the amplitude of 3. You're going to see that the highest this goes up is that 5 units. Now, when we hit pi over 2, we're at the maximum. Notice that we are still having positive R values as we enter that second quadrant. And notice that until we hit, let me scroll this over here. Even when we hit pi, we still have positive R values. While they are decreasing, they're still positive, which is why when this angle enters the third quadrant, the R values are still on the solid green line. Now, note what happens when we get to this value right here in between pi and 3 pi over 2. This is an x, don't change the graph, get the button, there we go. This is an x-intercept value. What's true when we hit the x-axis? The R value is 0. So as a result, when you hit that x-axis, your R value 0, you return to the pole at that value. Now notice for this graph, there is a short period of time that the R value is negative. So what's going to happen is we are going to look at the solid green. We are at this angle that is still in the third quadrant, but because our R value is negative, it's going to graph on the dashed line. And notice that we're going to hit this like smallest value, but distance-wise, it's an R value of 1 away from the origin. So you'll notice that the inner loop is being created from x-intercept to x-intercept here. So you can see that when we hit that x-axis again, it's going back to the pole. So that little piece that goes underneath the x-axis is what's creating that inner loop. And then notice to complete the graph, we can keep moving here, and then we can return to where we had begun when we get to 2 pi. So hopefully that helps you with understanding that creation of the inner loop. For problems that have the same exact A and B value, let's see if I can do this. I'm going to change that to a 2 sine t. Let's hope this works. And then I'm going to go back to the beginning. Note that in this case, we don't dip below the x-axis. In fact, our R value never goes negative. So when you are at the starting point, we're at 2, we reach that maximum still at pi over 2, but notice that when we get to 3 pi over 2, we just hit the axis. So notice how your graph creates this rounded region and it hits the pole, but then instead of creating an inner loop, because now our R values go back positive, notice that we're on that solid green line, but it doesn't create that inner loop. It creates that rounded heart-shaped region, and this will always happen when the A and B values are equal. Even if you change the sign in between to make that a minus, so make that a negative 2 sine t, and you go back to the beginning, notice how this affects it. You're just going to see that now you're going to start by decreasing to get to that pole, and then you're going to move away. Your R values are going to be positive up until you hit that value of 2 again. You may say, well, why is this happening that when I sub in pi, I'm getting this R value of 2, but keep in mind that you're going to see the same thing when you sub in 0 to the original equation. What is the sine of pi? What is the sine of 0? It's the same thing. It's 0. So then when you do 2 plus 0, that's where you're getting that value of 2 for those angles. Then as you move away, you're going to see again the R values stay positive, but now we hit this maximum at 3 pi over 2, and that maximum being 4, which would make sense that it's the amplitude value plus the midline value. And then again, when you get to 2 pi, you will finish that curve. So that covers the limosome with an inner loop, that covers the cardioid region. Then we have these dimpled limosomes. So I talked to you guys about how if the A value is larger than the B, so let's change this now to a 3 plus 2 sine t. And let's go back to here. Think about how for this graph right here, let me scroll down here, your midline's at 3. Okay, so right now you are 3 units away, and then you're going to get to pi over 2, and then note you are at your maximum, midline plus amplitude. You're at the maximum for this one. And then as you, oopsies, no. It's so annoying when you do this. It's more annoying when you're trying to watch a video of me doing this and you're not doing it, but I am. Let's get back to that. Did it work? I think we're back, right? What is this Greek alphabet here? I didn't know you could even do that. That's good to know. But what you're going to see with this graph is that as you go around, we again don't ever have a negative R value. You're going to see that we're going to hit right here at 3 pi over 2, this value that represents the minimum of the sinusoid. But again, this distance of, 2 units, approximately 2 units there, or I'm sorry, 1 unit at this point, away from the pole. And then you're going to see that from there, as you trace, it's going to increase in the same way that it had decreased just recently to get to that minimum value, that value at 1. And then kind of going away to kind of create the graph. So you're going to see, I always, if we were in class, I always call this the poop graph, because it kind of looks like you took your finger to like a marshmallow and just went poof, or a cotton ball and like poop. I don't know. It's not like I'm pooping it, but like it kind of looks like you just like, indent it just a little bit for that dimple in there. And then this convex, this is how we all feel right now, like with, just giving up on things, and it's just like, whoa, you feel like a blob. But you'll see when that ratio is bigger. So going back to this graph, let's see if I can do this without having to, but make that 3 in front, even a bigger value. So if you make it, a 6, so then the ratio of those 2 is going to be 3. So it has to be 2 or more. You're going to see it starts getting more blob-like. And you can think about, again, going back to the graph and tracing Y, we have this midline at 6, but think about how we're not going that far away from 6. The farthest away we go is 2 units. So it's creating more of a circular shape as we go around. And then again, we're going to return back when we, get to that midline value. It's going to return back to 0, the axis. And then as we, continue to go down, you're going to see again, moving the 2 units away, it's going to make it look more rounded, because the change in those numbers is not as significant. So you're going to see, let's move in that, how it's going to get us to that value. I mean, think about subbing in different angles for t and how they're being affected, multiplying that by 2, adding 6, and you're seeing how that becomes more rounded there. So that is your limosomes. Again, knowing the different names of them is not as important as really just knowing what we call the cardioid, and just kind of what is creating this dimple look versus not. And it has to do with that ratio of the A